waiting for the others. Any question? Not for the moment. Okay.
They will have to give exam
Oh,
on 9th.
okay. Yeah. Very, very serious example. Yeah. Don't worry, it will be very, very straightforward. Okay. I will propose to start. The others will come, as usually, a little bit later. Well, it's not a problem. Okay. Well, as I promised you, I will speak you about solid state lighting now. What we seen this morning is legacy. It's still there. You have to understand what is and how to use it. But from the next years and the next decades, most probably solid state lighting, LEDs, will be the dominant light source. Maybe not 100% because it is very difficult to replace everything with LEDs. To give you an example, if you take an electrical oven, it's almost impossible to put anything else than an incandescent lamp inside because nothing will resist at the temperature of the oven. Okay? For now, we don't have any alternative solution. Well, as I told you this morning, there is a revolution inside. The luminescence was the LEDs. But in fact, you have to be very careful with the word revolution because, historically speaking, the revolution is rather old. In fact, the first paper speaking about luminescence from semiconductors is from 1907 and has been published by this guy, the Captain Henry Joseph Round, who was the number 2 of Marconi company in UK, and as it seems, this guy was playing during his time with different things, and I don't know how he arrived to do that. He polarized a crystal of carborundum. Carborundum at that moment was the name of silicon carbide. Well, we are speaking silicon carbide beginning of 20th century. And as you can see, he published that paper, 907, and he said the crystal gave out a yellowish light, but also in some situation, light green, orange, or even blue. Wow. This is incredible because today to get light out, as we will see from a semiconductor, you need a semiconductor junction. You need a PN junction, otherwise there is no reason to get any light out. But most probably he was lucky because his carborundum crystal had enough impurities to have a small PN junctions, natural PN junctions, inside the crystal. But getting blue light is really surprising because blue is one of the most difficult colors to achieve. And of course, Round, at that moment, he doesn't know many things about atomic physics, quantum mechanics. All that is under development beginning of 20th century. And he finished his paper by saying that he will be glad if someone who have seen the same phenomenon can contact with him to discuss about. I don't know if he has any contacts, but that is the discovery of electroluminescence, but the phenomenon has been called electroluminescence several years later, 1935, by French researchers in the Center of National Research in France, Georges Destriot. At that period, we don't speak about electroluminescence, as either we don't speak about electronician or electronics. Around, he was not an electronics engineer, he was a radio electrician. That was the term to design electronics guy till the end of the First War. Well, however, some interesting story here. 907 discovery of electroluminescence. 20 years later, 1927, we have a first patent, Soviet or Russian, I don't know what was at that moment, patent submitted by a radio electrician, L05, who said for the first time, we can use that no-name phenomenon, because it was not named at that moment, in order to produce white light and light up buildings. He was well in advance of his time, because we had to wait 1962 to get the first real LED, that was a red LED, and he was produced, fabricated by Nick Holonyak in the United States. Nick Holonyak was the first student of the guy who invented the first solid-state transistor. Okay? And after that, we had yellow LEDs, a little bit greenish LEDs, but never blue LEDs. We had to wait 1993 to have the first blue LED made by Suji Nakamura here, and Suji Nakamura got the Nobel Prize of Physics in 2014 for the invention of the blue LED with two other Japanese persons, Professor Akasaki and Hiroshi Amano. Those two persons, they don't do anything for the technology, but they wrote down some theory about the opportunity to use some kind of semiconductors to obtain blue light. The work is really done by Nakamura, and at that moment Nakamura was, as he defined himself, he's a very good friend, himself defined Suji as a small engineer working, diplomate from a small university in the periphery of Japan. He's born in Matsuyama, in the smallest island of Japan, and working for a small company. The small company at that moment was Nichia. And when he got his, when he realized the first blue LED, he had even not a master degree. He got his master degree later, and he do everything from scratch. Well, very interesting story. And Japanese people, they never recognize that a small engineer for a small university working in a small company can achieve a so big invention. 10 years after fighting tribunals and justice, he get out from Japan. He never came back with $100 million. But $100 million is huge for a single small guy. But if he had 0.01% of the revenue of LED today, most probably he got several billions for him. Well, okay, this is just for the story. In fact, Nakamura presents his first LED around 1994, 1995, and blue LEDs start penetrating lighting in order to produce white light. I will explain you how from 2000s, but the technology can be considered as mature from 2010. Before 2010, many people want to use LEDs, but the result was complicated. Even still today, we have some problems. Well, today we have two big categories of LEDs. I will explain you after how it works. You have the 5mm LEDs. Why 5mm LEDs? Because they have this characteristic shape with a dome, and the size of the dome is 5 millimeters. Okay, and you can produce any color and also white. This kind of LEDs, they are low power. You are staying here less than 500 milliwatts input power, and they produce very few light. They are not the good option for lighting. Today you can find some lamps that they are using such kind of LEDs, and you have many of LEDs in that lamp. It's absolutely not advised to use such devices. They are completely unreliable and useless. For lighting, we use the high power LEDs or high brightness LEDs. They have different forms, contrary of that. And in fact, what is inside, you have a crystal, a PN, two crystals, a PN junction of two crystals. I will show you how. After, in the middle here, on the top, we'll add a fluorescent material in order to get white light. You have the lead wires, usually 10 millimeters gold, 10 micron, sorry, gold wires. That was the first technology. Some other now here, they use gold micro balls in order to stick the chip on the board. And then you have primary optics, and you have also an important heat sink in order to evacuate the thermal power in excess. The size of the crystal for an LED of 1 watt is around 1 millimeter square, 1 millimeter by 1 millimeter. These kind of chips can go up, in a single chip, can go up to 5 watt. It was some 5 watt single chip LEDs produced beginning of 2000 by Philips, and they have been used, many of them, to illuminate the Shanghai TV tower. But finally, the 5 watt technology has been abandoned because it's very difficult to produce good quality chips for 5 watts. You need larger surface, and the efficacy is much lower. While today, we use mainly 1 watt chip technology, and you can have inside a single module, you can have maybe 50 chips, and in that case, you have 50 watt LED. There is how it works. In fact, you have a PN junction between two materials, N-type with excess of negative charges, and a P-type with excess of positive charges. Hole. If the circuit is open, nothing happens, because you have a potential barrier here between the two semiconductors, and that means, due to the diffusion, normally N charges want to go to the other side, and P charges to the other side, but the potential, the barrier potential forbids this diffusion, natural diffusion thing, and nothing happened. Now, if you add a small DC voltage above the threshold for the PN junction, then you lower the potential barrier, and you open the door. You open the door, and negative charges can go that direction, positive charges go to that direction. You have a DC current flowing inside the PN junction, and in the middle here, negative and positive charges, holes and electrons will meet, and they will recombine by producing light. The excess of energy is transformed in light. There is some more insight based on solid-state physics. If you have here the energy description of the material, you have a solid PN junction with a conduction band That means any electrons or negative charges here, which is electrons usually, here they can move and they can allow a current to pass through, and then you have all the valence band in the lower part. That means any charge there cannot move, stay at the same atom at the same position in the crystal, and between those two you have the gap. Okay. Now, when you start feeding the LED, you allow electrons from the conduction band to pass to the other side, meet a hole, and then you have a photon coming out. This photon is coming out in a given frequency, which is corresponding to this energy value. But you can allow also an electron here to come and combine with a hole there, and that means you will have another photon with a frequency nu2, which is slightly different from the first one. That means if you look that, an LED, because you have only one system, can produce a single wavelength with a width, a small width. Usually the width here is in the order of 10 nanometers, which is very, very small. It's not like a laser. A laser is even thinner, but here is still almost monochromatic. And what you can get, the central wavelength depends on that value, and that value is dependent on the material that you use. And as you will see later, there is a big problem. We have materials able to produce red, able to produce blue, but green is very complicated. We don't have materials with a direct gap corresponding to green wavelengths, and this is a very important problem today in order to achieve highly efficient white LEDs. There are some ideas to use indirect gap materials, but you have to design the material. It's not materials that you find like that around you in the nature. Well, the spectral wheel is very small, and the color changes with the junction temperature. This is important. You see that this energy difference is proportional to 1.8 kb Boltzmann constant T, the temperature of the junction. It's small, but could be noticeable by the human eye. If an LED hits his wavelength, the color shifts. And you see here that the N max, the maximum here, this value, depends on the gap, but depends also on the temperature. And this may be problematic, especially for lighting, when you need to have a fixed wavelength to get a good quality of light. And as I told you, this is the famous green gap problem. All the materials that we have today based on indium, aluminum, gallium, indium nitride composites, that was the idea of Nakamura, can produce especially blue and violet. But if you change the concentration in indium, you can go towards green, but the efficacy is reducing. From the other side, if you use aluminum, gallium, indium phosphide metals, that alloys, that was the idea of Nick Holonyak. You start from red, and you can go by playing with the concentration of phosphide. You can go through green, but once again the efficacy drops, and there is nothing very efficient in that area. Small problem. Remind our eye, the maximum efficacy of our eye is in the green area. Okay, you understood very well that LEDs can produce monochromatic light. Okay, nothing else. How then we can produce white light? how the LEDs that they are here, how they produce white light. You need to cheat. There is not only only possibility, but there are several ways to cheat. This is good. The problem is when you cheat, you pay somewhere, and you will pay that in the efficacy side. Okay? Well, first way to cheat is to mix red, green, and blue. Remind our eye is sensitive to red, green, and blue. If you set red, green, and blue, okay, you can get white light. If you combine those three colors here and you take the barycenter of this triangle, the white that we'll get is here, okay, which is neutral white. But you have a number of drawbacks. First thing, if you use only 1, 2, 3 colors, you can reproduce only the colors that they are inside the triangle that we call the gamut. All colors outside of the triangle impossible to be reproduced correctly. Other thing, if your green, which is very unstable, switch from here to here, the difference in the wavelength is not enormous, then the barycenter pass from there to there, and you go towards higher correlate color temperatures, which is rather unacceptable. We don't like to have color temperatures above 6,000 Kelvin. It is very cold. It is very, well, people, they don't like it for interior lighting or any kind of lighting. Then, of course, you have poor color rendering, because you can render correctly only those 3 colors. The remaining will be not very good, and the color render index of the system will be bad. And also you may have significant optical losses. Why? Because you need to mix the 3 colors. You need to mix the 3 colors and mix them effectively, because if you have 3 sources, which is a little bit distant one from the other, and you have an object, you will have 3 shadows, and the problem is the shadows, they are colored. And this is very unpleasant for people working with lighting. You can see that if you go to some shopping malls. Sometimes you have different type of lights, and then look the shadow, especially if you have a white floor. You can see that you see 2 shadows with different shades, and this is not very very good. And also, the color control is not intuitive at all, because you have 3 parameters to fix: the red, the green, and the blue channel. And if you want, you can add more colors also, and that makes the life more complicated. And this is just for fun. It was an idea from a big Dutch company. Well, I can say the name now, Philips, they don't do that. And the idea was, okay, making white light with that is complicated, but let's make something fancy. Here you have a lighting system with red, green, blue LEDs inside. Here you have a small instrument that is able to measure the color point of an object, the cow here, and the light, the fixture takes the same color than the object. If you have a nice blue tie, you show your tie, and the lighting will become blue. Well, this is funny, but it's not for lighting. It's for decoration. And today we use mainly 3-color mixing to obtain different colors, and even we use much more than 3 colors for scenic lighting in order to make different colors, different ambience. But the day that we could have an efficient and stable green, most probably this will be the best option to get white light in the near future. It will go beyond the method that we use today. That you have to know also is, if you go in Louvre Museum, you have Gioconda, the famous painting from Leonardo da Vinci. Gioconda is illuminated since 15 years now by using LED system that mix initially 7 colors. Today they mix 256 colors. and they mix that using torsadate fibers, and they eliminate the painting, and the idea is to keep the green colors as it is in reality and change the color of the skin to a real skin color, because the painting is very old, never been cleaned, and the varnish that they put on the top, Leonardo put to protect the painting, becomes yellow, and if you see Gioconda without the special lighting, you think that you see a dead guy, a dead person. The color is completely yellow for the hands and the face, and the lighting system using different LED colors correct the effect of the aging, but not touch to the green colors or characteristics of the painting. Well, okay, let's go. What we use today to produce white light. It's very interesting when you have this color representation, this we call CIE 1931 color triangle. In principle, all colors, light colors, are inside that triangle. The saturated colors, the colors of the rainbow, are in the periphery. In the middle is the white and the blue, the black body locus. And here some colorimetric principle said that if you take two opposite colors and you join those colors, then you can mix them and you can obtain any color in that line. Look well, if you take yellow and blue, you can pass through the white. That means if you mix yellow and blue only, you can obtain white. There is not other solution, because if you want to mix green, you need to use purple, and it's impossible to produce purple with light sources, only with filters. Well, the only solution is blue, yellow. That because the invention of Nakamura was very important, and I will show you that. Take my material. Well, this is a blue LED, such invented by Nakamura, 5mm LED. You see, doesn't eliminate anything, but this is not a problem. And that, here this is a piece of plastic. In the front, there is a thin layer, a film of luminescent material that can absorb blue and emit yellow. That means you send blue here, you add yellow, and you can obtain white. Look, you can switch off the light, maybe it's okay. And I'm showing you that direction and not that one, it works also. But do not confuse, it's not a filter. It absorbs the blue light, reflects a part of the blue light, plus white, plus yellow, and you obtain the white somewhere in the two. You have white, but this is more reddish. It depends on the wavelength. It's not the same wavelength. That's more violet than blue. Both that and that, they are invented by Nakamura. And Nakamura today is using more violet lasers to produce white light. High range cars like Ferrari, Porsche, Mercedes, or Audi R8, BMW, now they have headlights no more with LEDs, but with lasers. In fact, you have lasers, blue lasers emitting, and the light is coming to an oblique side to the material, and then you have a white LED beam. And what is the difference with lasers? You can have high beams going up to 1 kilometer. LEDs can go up to 400, 500 meters. Classic lamps can go up to 200 meters, no more. And of course, if you can see further, you can anticipate some dangers. And here, if you play with the different material, look, here you can have all the colors. And the top, here, you have different color temperatures because you are changing not the blue LED behind, but you're changing that. Look, if I take my laser and I spot the LEDs, here you don't see any reaction. Look here. The LED responds to the blue light. Okay? Well, this is the way that today we produce white light for any kind of lighting applications, except maybe for some applications for theater or decorative applications. Okay? Well, someone asked me yesterday about, no, in one of the open talk, the influence of blue light on the eye. If I send you the red laser in the eye, you will not appreciate. If I send you the violet laser here, I can destroy a part of your eye. Okay. Let's continue, and this is the way that it works. The blue chip, and on the top, initially we put the white phosphor, the yellow phosphor, and you obtain white light. But initially had some problems. The conversion was very low because you had to have, this is the emission of the blue LED, and you have to find materials that they have enough overlapping with the blue area. And beginning of 2000, all the phosphors was more made for fluorescent lamps and responds to UV than in blue. And this overlap area was very small. That means the efficiency was very low. Another problem, you had a color halo phenomenon because the LEDs, like lasers, by their physics, they are directional. Not only they have small width, but also they go to a given direction which is perpendicular to the junction. Okay? And if you do that, then you have the blue light here is like a beam, but the phosphor who absorb the light then emits like a Lambertian system. One is a beam and the other is Lambertian. And what happened? If you look from the side, you see yellow. If you look from the top, you see blue, and the result is not very pleasant. Now we completely solve that problem. Inside to put here the fluorescent powder of the top, we put layers of the fluorescent material to a conform way on the top of the crystal. We coat the crystal with a given uniformity in all sides, except in the bottom, in order to avoid that phenomenon. And this needs a lot of technology development. Same thing, initially only two colors, very bad color under index. Today this problem also has been corrected by adding additional materials here that can add some green, some red, and you can correct the color. And also initially the color temperature was rather high. The third way to get white light, this is that Nakamura is suggesting now. Nakamura is 70 years old, but he is still active. He is professor in UCLA, in California, no, Santa Barbara, sorry. And he has his own company, Sora, and this is the concept that they try to use today. They use violet LED chips, no more blue, and on the top they put three kind of phosphors, green, yellow, and red, green, blue, and red, sorry, and they can get very flat spectral distribution, and this is a very good white light, and this is can be used for automotive, for general lighting, or even from agricultural lighting, and here we can achieve CRIs as high as 95. When normal LEDs can go up to 80, 85. What are the advantages of LEDs? All what I will say now is true. No problem. But you will see there is difference between the truth for the component and the truth for the LED lamp. This is very important. First thing, they are very bright. They shine everywhere. When you see that, it's very bright. But bright doesn't mean you eliminate something. If I put in front of my eyes, I will be glad, but something shining doesn't always illuminating. Remind that. It's like gold. Something like gold is not gold. Okay. You have excellent saturated colors. Blue, green, yellow. Yes, but for lighting you need white. You have high luminous efficiency. Efficiency, I remind you, this is the radiometric quantity. Radiative power in watts divided by electric input power in watts. Today, for white LEDs, we are around 30 to 40%. For blue LEDs or red LEDs, we are around 90%. And in theory, you know how much is the theoretical higher efficiency? Radiative efficiency. Say a figure. 100? 100%? Why not? No. It's 105%. You tell me he is crazy, 105% for efficacy, for efficiency, sorry, is not possible. Yes, but remind how efficiency is defined. Radiative power in watts divided by input electrical power in watts. If you can inject additional power in your LED, then you can get more radiative power and the ratio is higher than 1. And where is coming that power? Today, this phenomenon is proven, but it's very difficult to use. If you have a pure crystal without any defects and at very low temperature, the semiconductor is the only system that can turn 100% of current in light. This is a known phenomenon, very difficult to obtain, but it is known. And George Crawford, one of the guys that he invented, also the co-invented the red LED, he said that, and now it is proven, if you have 100% conversion from electricity to light, the junction pumps heat from the environment and transform the heat to additional light. That means one day, if we can have such kind of components, but most probably we'll never get that, we can have also lighting and air conditioning. Not only you light up, but you cool also the air. Yes? No. Well, this is also cheating because the definition is emitted power over electrical input power. If you say radiative power over electrical plus other inputs, then you will get 100%. Okay? But if you stay in the formal definition of radiative power is the electric input and the radiative output. In that case, you can go more than 100%. But in any case, if you can achieve it, you can put blue LEDs in your fans there. They will transform 100% of electricity in blue light, and then they will pump also heat from the environment as a heat pump to produce more light. But, okay, the phenomenon is proven experimentally 5 or 6 years now, but it's impossible for the moment to turn it in a commercial product. Okay. I continue. High energy efficiency, you speak about that. High luminous efficacy, not efficiency, I have to correct that. We can go up to 200, even more lumen per watt today. Robust, yeah. If you take the small components, You can throw it, you don't make anything. You can walk on the top, same thing, still continue working. Now if you take an LED lamp and you left it drop, you can crash the lamp. It's not the same thing. Long lifespan, yes. If you operate the LED in a fridge or in the North or South Pole, most probably the life expectancy of the LED itself is more than 100,000 hours. Now, if you are in a real system rather hot, like here today, or if the system overheats due to bad thermal design, then the lifetime of the LEDs will drop. Usually today, 25, 30,000 hours is a realistic value for LED systems. For the LED, the problem is the power supply behind the driver. You have low supply voltage, okay, you need such DC low voltage, few volts up to 10, 15 volts is enough. Easy to feed, yeah, okay. You start from AC, you have a rectifier, and then you send the current, a filter, and you send the current to LED. Yes, this is I am physicist at the origin, and this is the simplest way to represent an LED driver. In reality, an LED driver is much more complex than that, but always it's much more easy to control than any other kind of lamp. We will discuss about that tomorrow. And of course, they don't produce any UV or infrared. This is very good, for example, to illuminate museums with different sensitive things that they don't like to have exposure to sunlight or things like that, or even could be the best option for some people with orphan illness that we call the kids of moon, people that cannot go even outside. The UV from the sun will completely destroy their skin. Those people, they accept only today incandescent lamps, but most probably LEDs can play the same role. Yeah. This is just a historical point of view. At the beginning, 5 millimeters LED, they emit 1 to 2 lumens. And you see here the evolution up to 1,200 lumens in 2007. And this guy here, Hates, announced a rule, said that luminous flux is multiplied by 2 every 18 to 24 months. And this is during 30 years. This is the equivalent of Moore's rule for printed circuits and integrated circuits. But now, unfortunately, Hyde's law is finished. We achieved a plateau. It's much more difficult to continue respecting his rule, but it was valid for 30 years, not bad. And I remind you that 1 to 2 lumens or 1,002 lumens, 1,000 times more, one candle is 10 to 15 lumens. How you can find that? One candle is one candela. If you assume that emits the light everywhere in the same direction, the 360 degrees space is equal to 4p, and then you have 4p times 1, you find 10 to 15 lumens. That means this one is the equivalent of 1,200 candelas. Well, LED performance is still increasing. I told you that at the introduction. You can see here the record values, the maximum values achieved. Today we have some LEDs, white LED chips. I'm not speaking about lamps, with 303 lumen per watt luminous efficiency. This is good. And if you look what happened with the different kind of technologies, here you have incandescent and halogen lamps. Here you have compact fluorescent, different other discharge lamps here, and here you have the white LEDs. Everything here is going to a plateau. white LEDs continue increasing, and this is the most efficient lamp that we have today. That is the chip. Here is the lamp. I will explain you how it works. Is that we call the LED filament lamp, and achieved more than 200 lumen per watt in 2017. Today we have a little bit more. And here you can see that for lamps or for downlights, always the luminous efficacy is increasing. The different lines, they are just quarters of the different products that we can find registered in international databases. The yellow line is the best 5% of the products, and the line here, this one, should be beyond that line. You have 80% of the products. And the question is, okay, it increases everywhere. Where are the limits? Because limits exist, and this is the projection from the Department of Energy, DOE, who predicts what will be the limit for white LED lamps. We are not speaking about components here. And you can see that if you take conversion for obtain cool white, maybe in 2050 per watt. If you take here, that one, the yellow line, is blue white, and this is for warm white. Warm white today is a little bit less efficient than cool white, but we expect to achieve the same values later. And then you have other technologies. Here the green one is that we call the hybrid technology. That means what? That means blue-yellow chip plus a red chip together inside, red LED, couple blue phosphor plus red, and then you can go up to 290 lumen per watt. And the day that we'll have efficient green LED, this is RGB mix, red, green, blue, you can achieve maybe more than 320, 330 lumen per watt in the next decades. However, those values are good, they are excellent. I remind you that a T5 tube, which is the more efficient, is 110 lumen per watt. Here we are 2 times more, even 3 times more. The problem is which luminous efficacy are you speaking? Because you have the luminous efficacy of the chip, the luminous efficacy of the lamp under standardized conditions, and the luminous efficacy of the system under operating conditions. And this is the trap. Let's look together. Let's take a very simple example. From LED, we integrate up to a full lighting system. Let's take an average quality, today white LED, cheap, with 130 lumen per watt. This is very cheap, you can find everywhere, it's reliable, no problem. But one LED like that is 1 watt. It produces 130 lumens, okay? Because this is the efficacy. But to obtain enough light here, you need at least 1,200, 1,300 lumens. That means you need at least 10 chips together. And those 10 chips you have to integrate in a module, and then you have to evacuate the excess of the calories. And you have to avoid that when this chip overheating, influence his friends all around. You have to have a good thermal management design. And from here to here, you will lose at best, 8 to 15%. Then you have to use optics. Optics to focalize or to distribute your beam as you want in order to be able to illuminate a surface. Here, optical losses, if you use high quality optics with silver coated glass reflectors that cost a lot of money, you will have between 5 and 20% of losses. That you have to know. Sunlight coming through a simple window lost 10% of the power. That's because the windows overheat. This is a good value. Then you have to drive. And the driver, you are a specialist here, they have losses. Excellent drivers, DC-DC converters, can go to few percent. Good quality AC-DC converters, simple one, can go up to 50%. Bad quality can go up to I don't know what. Forget it, or you double, you triple the power that you can put inside. And finally, all that is inside a fixture, like here. We'll discuss about fixture tomorrow. And a part of the light is blocked inside the fixture. A very good fixture has photometric losses in the order of 5 to 10%. Now, if you start from here and you apply those values in cascade, you will find that the plug-in wall, the wall plug efficacy of the system will be something between 100 and 55 lumen per watt. You start with 130 and you arrive here. 100 is comparable to a T5 tube, that's okay, but 55 is comparable to a CFL lamp, is very bad today. The way that you use your system and the way that you integrate the components, the elements of the system, and the different parts of the system that you will use is very critical in order to achieve high luminous efficacy at the end. And when you make lighting, I don't care about that. I'm interested about that. And what happened, many people that today sell, unscrupulous people that say sell LED systems, you saw calculations by using the value in lumens per watt of the chip that they integrate in the system and never the real value of the system. When I see lighting systems like that and the guy told me 150 lumen per watt, I don't believe him. A system like that can achieve maybe today 100, 120 lumen per watt, except if you have 300 lumen per watt LEDs behind, but this doesn't exist today. Okay? Well, you have to be very careful, and you will see there are some other issues that you have to take into account. Okay? Be careful that between chip and system efficacy. Other thing also, the efficacy and other parameters depend strongly also on various other parameters. One is on the wavelength that we told. This is the green gap, okay? When the junction temperature increases, in all colors, the light quantity is decreasing, the brightness, the flux. When you increase the current, you increase the number of lumens, but you decrease rapidly the number of lumens per watt. If someone told you my LEDs, they are 120 lumen per watt at 400 milliamps, if you boost the LEDs at 400 milliamps, if you boost the LED at 1 amp, you will not really damage the LED. They produce much more lumens, but then most probably the efficacy will be less than 80 to 70 lumen per watt, which is not interesting. Never boost LEDs beyond the value that is given by the producer. And also same thing, when you increase the emitting surface of the chip, you decrease the efficiency, and that was the problem between the 1 watt LED and the 5 watt single chip LED. temperature, several effects. One, when the chip hits, you see here the wavelength length is shifted and the width is changing. Here is exaggerating. You pass from -20 to +85. But what happened? When you overheat, the blue is shifted to higher values, and then the surface here reduces. That means the phosphor produce less yellow, and finally all the system produce less light with lower efficacy. Same thing here, very important. If you don't control the current inside your LED, you may have huge problems, because what shows that graphics here is when temperature increases here, from here to there, the voltage threshold is decreasing. And if the voltage threshold is decreasing, as you are in the exponential part of the diode, you increase very rapidly the current. Well, some time ago, some very clever guys, like Steve Jobs, don't speak about him, wants to make by yourself in your garage, and they recommend how to replace LED with LED classic fluorescent fixtures. And the guy said, no problem, take a plate of wood, drill holes, put the LEDs there, you make all the cables, and if you put enough LEDs in series, you can achieve a voltage going up to 220, and no problem, you can put it in direct in the plug, or if you want to put less LEDs, just put a resistor in order to stabilize the current. The system will switch on, no problem. If you do that, you can achieve something that is operational. But what will happen? The LEDs will start heating, especially if they are inside the hole in the wood, which is well isolated. And if they overheat, the threshold value voltage decreases, and the LED calls more current. As behind you have all the nuclear reactors of the country, you can provide as many power as the system asks you. And if the system asks more power, it will heat more. And you go to a problem that at the end the temperature will be so high, and you will have fire problems in your installation. And this is not something that is just imagined. It was the case. We had systems like that they took fire by themselves because the system was completely uncontrolled. And of course, you decrease also the lifespan. Well, to avoid all those problems, you need to evacuate the heat. If you take an incandescent lamp, remind you, 5% at best is light. All the remaining 95% is heat, but 83% of that heat is radiated as an infrared radiation. No problem to evacuate, and only 12% is evacuated by the rear part of the lamp, by the socket. In LEDs, if I take a good white LED, 35% is light, and the remaining 65% is heat. 1 watt, 650 milliwatts thermal to evacuate. Now, if you have 10 LEDs, you have a 6 point something watt to evacuate. Okay? And to evacuate heat, of course, you can use a radiator. If you have 1 watt, this radiator is okay, but if you want to eliminate a street with 50 or 100 watt installed LED power, you will need that as radiator. It's not the same size, and when the temperature of LED increases, his efficacy drops. That means you need to evacuate more heat. The solution to that is maybe today to use more customized radiators, and also maybe go to ceramic material radiators. This is another solution in order to make less bulky and less heavy, but it will be never possible to read out the radiator, unless the day that we will have 100% of light here, but it's not possible because a main part of the losses here is due to the phosphor. Passing to RGB, maybe it will be easier to manage thermally the system. Other problem, quality. Look that, you see the chip, they are not soldered correctly. Look here, this is the input voltage, and this is the measured current. Inside the system you have spikes. This is completely against the IC standard for harmonic distortion. Normally in Europe we cannot have more than 5% of harmonic distortion in LED systems. This is absolutely impossible. You have hotspots nearby chemical capacitors. Here you have the transistor. Here you have two capacitors that will collapse very rapidly, and your system will be out of order. That means such kind of systems, they have really very bad design. Even if the LEDs, they are very good, sometimes the LED can be very good, but if the design is bad, you can see here poor manual welding. Normally the soldering has been done by machine, not by hand, but in China or things like that, when they produce LEDs at very low price, they do it manually because the working power is not very expensive there. Hazardous wirings, the wires can disconnect, and then you may have, of course, electric hazard. Low quality capacitors, especially in the bad place. Poor mechanical qualities, and also hot spots in critical areas. And when you have such products, even if you buy them at very low price, finally the general public refuse the products. This is a coupon from Indian journal from 2014 that saying clearly, stop, don't sell anymore so low quality products. Even if in Indian market people prefer cheap products at very high quality products, there are limits, okay? And then you have a very nice problem and very nice issue. When you have someone coming to you as telling, okay, please buy my fixture, my lighting pole for the city. You see, you will be the best one. You will have high efficacy. You will achieve everything, even your coffee if you want. No problem. And if you ask those guys, is your system certified? Oh, yes, of course. I have certificates. This one, you see the photocopy, is a certificate that I recovered in France maybe 10 years ago in the frame of a dispute between a small village and a company. In fact, I will explain you. The company producing usually Christmas tree lights, they decided to produce street lights. They bought a container with LEDs from China at very low price, and they start making integration of LEDs without any necessary knowledge how to do that, okay? And this factory, a small factory, was located in the village, and the director of the factory was friend of the mayor, and he told mayor, please buy 2 or 3 of my luminaires and put it at the roundabout in the entrance of the village. All people will see that, it will be a big publicity for me and also for you, because you will energy, you will be a green guy and all that stuff. But I cannot give you the fixtures because they are expensive. You have to buy, but today the French National Energy Agency will give you 90% of the price return back because you are making energy savings. That was the legislation. Well, the mayor passed through his council, they accept, they bought the 4 luminaires, they put it there, and the mayor, as like politician, starts to make communication in the local journal. Look what my community is doing, and we'll get 90% of the money back. And then the next level politician who goes in charge of the departmental agency of energy, and he is assumed to give him to the other 90% of his investment, was not in the same party, of course, and he said, well, who tests the system? Who can certify that you really make your that energy savings? And he sent technical people to inspect the system, and they found a system that was completely out of any standard, including electrical hazard standard, insulation, and then the departmental agency said to the mayor, 0, return money. Your system is not conform to any legislation. Because the mayor was not happy, go to see the company, and the company said, no. He says, we have this certificate that shows that our LEDs, they are very good, there are no problem. Well, and they were ready to go to the justice, and they called me and they told me, can you please see what happened here? And I took the certificate. First thing that I found is here, you cannot read it here, but no problem, you can trust me. There is a number of European standards or international standards that the certificate cover. Okay, fine, but the problem is that none of those standards is applicable to LEDs. First point. This is a CE certificate, European conformity. For a European conformity certificate, you don't need to have a certificate. CE label is just declaration. You don't need to have a certificate for that. Okay, forget it, that one. And then I discussed with other colleagues, we found that very curious, and we say, where is located the lab that he certified that? And here you have an address, and if you go to Google Maps, there is the address. Do you see any building here? The laboratory is not existing. And a few years later, when I have time, I'm looking in the web to find different new things, and I found a nest of certificates in a Chinese company. You have a copy here, another one. Same thing, different standards, nothing to do with LEDs. Same address, a very beautiful red stamp, similar to the stamp that I have in my passport each time that I go to China. And like false money, the same serial number of certificate. Well, never believe certificates unless if they are certificates coming from national authorities or for accredited laboratories. And even like that, you may have problems. We found a certificate stamp TUV, TU 2 points V, which is the national certification of Germany, declaring stupid things like that. And when you read the certificate, you see that it's certified by the TUV office in Beijing, in China. Okay, why not? It's an international organism. They can have an office in China. Well, we send a mail to some friends in the metrology authority in China. Do you have a TUV in China? Answer in the 5 minutes, yes, yes, sir. They are located in Shanghai. TUV in Beijing is not existing. It was a true false certificate with identity usurpation. And you have to be very careful. When someone comes and from the beginning show you certificates, don't believe him. Take a copy of the certificate, send to me, and I will tell you what I'm thinking about. Okay? Another problem also with LEDs. This is no more linked to the quality of the LED, but is linked to the lighting installation. The installers, when they install LED systems, do they understand the technology? This is very important. Here we have a pool from 200 something 100 in the frame project financed by the French European Energy Agency, and the pool has been conducted by a guy who buy lighting systems from the manufacturers and sells then large quantity systems to the cities and things like that. That means all people here answer to the pool with true answers. Okay? We ask them, that is maybe 15 years ago also. Today the situation is much better, fortunately. We ask them, do you have installed a lighting system? Yes, 90%. Okay, great. Among you, do you have problems? Do you experience problems when installing LEDs? No, sir. Everything is working perfectly. Good. And then a number of other questions, and between the questions, some technical questions. For example, what will happen when the LED temperature will increase? And you can see the answers. Sorry, I forgot to translate. The life expectancy will increase. Oh yeah, right. False answer. Ah, this one is correct. The life expectancy will decrease. Okay, this is fine. Then here, the guy tells, or the person tells, the output light will be warmer. No. Or the output light will be colder. No. I will have more lumens. No. Less lumens. Yes. Well, when you see that, that means the installers, they don't master the technology. And what they will do, they will take a very good LED fixture, they will put in the roof, and they will put all around insulation in order to keep the fixture as warm as possible. And of course, a very good fixture under those conditions will be destroyed very, very rapidly. And this is not the problem of technology, it's the problem of the installer. That means what? That means simply that you need to train the professionals. And this is something that is very important today. You need to train lighting professionals to the new technology because they don't master the technology. And the principles of the old technology doesn't apply to LEDs. This is another problem. Blue light exposure. As I told you, if you get blue light in your eye in sufficiently high dose, you can destroy a part of the retina. That you can see here, the retina is completely burned due to blue light. I assure you this is not a human eye, it's a rat eye. But the retina completely gone here due to a high exposure and high dose of blue light. LEDs, they have blue light, okay? These LEDs, the LED that I show you, have blue light. Well, potentially they are toxic for the human retina. But in fact, this is not absolutely true because it depends on how much blue you have. If you have cold white, it's more dangerous than warm white. Warm white is not a problem. But the question here is not how much blue you have. The sky is blue and doesn't harm our retina, but it's a question of luminance. If the surface is large, for the same flux, you have less luminance, less brightness, and then to have a problem with those lights, you have glare, if I look it, but I needed to stay looking the light at least for 3 months without blinking my eyes in order to have a damage. Okay? Now, on the opposite, if you have a high-class Mercedes or BMW and BMW, and you have a kid in the trail, and you pass in the front of the car when the daylights switch on, and there is high blue content, then the kid can get the lights directly in the eyes, and the crystalline of kids is very clear to blue. Above 20, the crystalline becomes more and more yellow and protects our eye. In that case, you may have some trouble for the eyes of the baby. Another problem is when you buy toys with blue LEDs, and sometimes the kids made the eye on the blue LED. This can be also dangerous. Well, globally, today we don't really find in the market products that they have problem. I'm speaking about lighting products. Toys or things like that, yes, we may have some problems for the retina. And another problem is that blue light can also, this is nothing to do with the retina, can perturb your circadian clock. We'll discuss about that in another sequence. And if you receive a lot of blue light, the moment that you want to go for sleep, you may wake up and the result is not what you expect at the end, and you may have some other health problems. What next? I don't know what will be next. Very difficult to say. Sorry? Five what? I finished. This is almost the last one. Okay, and then we have break. Yeah. Well, what we can do, if I take the blue-yellow technology, we expect to go to 150 lumen per watt. You see there is very few to win in all potential losses. If we go to color mixing, RGB, we can go up to 330 lumens. Here we have some more gains potential with the technology. Some other ideas is to use nanowires instead of 2D flat chips. And here you can, inside the nanowire, have different dopings as function of the high. And you have, for example, red here, blue here, yellow, green here, and so on. And you can get from the nanowires native white light, mixed white but native. The problem is this kind of nanowires, they are very close each other, and if you want to avoid sparkings, you have to limit the voltage, or you have to put in between the pillars to put insulating material. But if you put insulating material, you don't leave the light coming out. The problem is rather difficult to solve. You see here a prototype of such kind of LEDs. Yeah. How much I have? I have just two more and I finish. Okay. Well, here you see the more recent innovation is the famous LED filament lamp. Here, in fact, what is a filament here is an alumina sapphire stripe, and on the top you have COBs, that means chip on board LEDs posed on the sapphire, and each one is connected to the other in series, and we cover all the stick with phosphor, and we have something like filaments. Okay, we can have any kind of shapes, we can even write things, have different things there, and also we have exactly the same shape with an incandescent lamp. And there is a relation with a incandescent lamp, because inside here, inside the bulb, we put nitrogen in order to collect the heat and transmit the heat to the wall and then to the socket. Same way that an incandescent lamp collect heat, and this can achieve more than 200 lumen per watt with very long lifespans, and can be used for general lighting, but can be used also for decorative lighting. If you go to bars, you will see such kind of lamp at very low level, but creates a mood, an ambience. Okay. The last but not the least, LEDs use raw earths. Indium, cerium, europium, and even gold and silver. And in that case, the problem is that our resources, they are not extensive. And if you take the indium and you see the indium price is oscillating because you have a crisis, you have more demand than potential production, and the potential production is almost constant. And that means if we go that way, we will not have enough indium to cover all lighting industry and even all electronic integrated circuit industry, especially because we don't know how to recover indium from the chips that they are no more in use. It's very complicated to recover the material because you have some ppms or even some bpms of the material, how you can get it back. This is a problem, and we needed to think about a good way to recycle, and this is a positive thing. This is a slide. When you go to some really poor areas that use that for illumination, if you can use LEDs with frontal LEDs with batteries that you can charge with photovoltaics or things like that, then one of the best effects of that is you allow kids to read in the evening and go to the school, and this has no value. It's not possible to say how much I won or I lost, but the education has no value. And if you do that, you can allow kids to go to the school, and you can see what said a headmaster from a school in a village in Indonesia. Where is the problem? Simply is that one costs a lot of money to the family, and the family will reduce the use of light in order to be affordable. With white LEDs that they can buy with a microcredit system and supply by photovoltaics, they can charge them, and then the cost is much lower, and this allows to the kids that they are working in any case in the fields in the morning to go to the school and study in the evening. Well, this is one of the very positive things of LEDs. And finish. I stop here. Thank you very much. And if you have questions, up to you. You understood everything about LEDs? No. That's good. You will ask questions later. Okay? Well, thank you very much, and see you tomorrow at 10. Yeah. Yes. Yeah. Blue color, or okay, it's not white. Okay, yeah. I don't know about that experiment.
Uh, but that zone was a sort of criminal zone. But after using the blue LEDs, the crime rate decreased there.
No. This
So
I don't believe that. If you have some reference, I want to look globally. When you illuminate better an area, you can reduce theoretically accidents and criminality. First of all, in Japan, criminality is zero. In Japan, if you lost your mobile phone, never think that someone stole it.
Yes.
Someone will find and will get back to you. You can leave something, you can find it. I lost a packet of Kleenex, you know, I lost it in the subway last week in Tokyo, I went to my place and I came back and I see my packet nearby the place that most probably I lost it. It was there 2 hours later. Someone put it aside.
Okay.
Well, no, in Japan there is no criminality, or there is control criminality. This is
So
another
hence for
point.
the,
No.
yeah.
The blue light, I never heard about blue light for that, and I never heard, no. But there is another option, which is if you go to nightclubs and you go to restrooms, usually they are illuminated with blue lights. You know why? Because you cannot find your veins for drugs. To avoid people going for drug in the restrooms. This is the only application that really I know anti-criminality, but
Okay, so that's why they asked to. I asked whether it is true or not.
yeah, if you find a reference, I want to see it. Maybe some that I don't know, but no, for me it's almost. Yet you told me Japan and criminality is not compatible. And second, I never heard about blue light illumination for streets. Yes, but I heard blue light in the disco areas for the bathrooms. Yeah. Okay. Any other question? Okay. Then see you tomorrow at